Hi, my name is Hayden Kaliji, and this is Fluids Project number 3 with Dr. Osbey. Uh, this is the 2D wind tunnel simulation. So, I am doing this project solo, hence why I have all 3 cases here. I'm going to, so in the previous projects, I did not walk through like the exact step-by-step setup of the project. It's specifically stated in this one that it wants that, so I will do that. I'm just going to do it for one of the frequencies, since all you have to do for the other two is copy the project and change the inlet velocity. So, yeah, let's get started. So I'm just going to insert a new fluid project. Right. And I'll just name this F20, let's just say B, yeah. So, starting our geometry, let's make sure this is set to 2D. Perfect. Okay. And we can start a new space claim geometry. Okay. So once you're in space claim here, you can here, we're just gonna, I don't even know why I was already sketching. We'll start a new sketch on the XY plane. We'll face it. And we can set this line as a mirror line, so we don't have to, do the entire thing. We can just make half of it. Oh, here, let's not make a line. So first, since we were given the dimensions of the wind tunnel in inches, I'm going to change this to inches. And then all the computation will still be like in SI units, so there's no problem there. So we can start here with an 11-inch line. Okay, and then we go over by 15. Let me pull up the, okay. Alright, contraction chamber, 24 inches, and then our test section has a height of 6. So we can go over by 24, and then down by 8, which will be 3 from the origin, which will be a full size or a full diameter of 6, or height or whatever. So, alright, so length of 12 here. Oh, sorry, let's put that in. So now a length of 12. Panel over so I can actually see. And we can remove these to over here. Delete. Alright, now for the diffuser. It has a length of 42 and then a half diffuser angle of 3 degrees. So we can start by going out by 42. Now, I'm sure you can dimension this in space claim. I don't really want to do that, so let's just use a low trig. So we can do tangent of 3 degrees, right, times our 42, right? It was 42, right? Yeah, times 42, which gives us 2.201126. We can just drop this in, and it'll be accurate enough, you'll see. So 2.201126. Okay, there you go. And if we drop this over here, you can see an angle of 87, which is 3 degrees, or a half diffuser angle of 3 degrees. So we can remove these here. Boom. Delete. Okay, drop a line in. Now, I will throw the dimensions in here just to show that everything is right. This is 11. Actually, you know what? I should probably do it like this. So 22. Okay, and 15. That's lovely. See, this guy's 15. Okay. Length here of 24. Perfect. Height here of 6. Length of 12 should be here. Right, length of 12, yes. Okay, it should be 42. Perfect, and have to use an angle of 3 degrees. Perfect. Awesome, so anything missing? 22, 15, 24, 6, 12, 42, 3 degrees. This looks perfect. Cool. So we can end sketch editing. It should fill in since it's closed. Now that is it for Space Claim. So let's open up our mesh. Here we go. Start by just generate. This doesn't really matter that much. So let's start with some sizing. We'll insert face sizing here. An element size of about, I believe I did 0.02, which is 2 centimeters. Now, if you do 0.02 or 0.002 meters, sorry, which is 2 millimeters, the computation will take quite a while. So I'm leading more on the kind of the bigger edge. So there you go. We can generate here. Looks good, okay? Now we're going to insert edge sizing. I did edge sizing specifically for the contraction here, and then the test section, just because of these like corners here. I was most worried about the flow being disturbed there, since it's kind of, well, where the most disturbance is, because the rest of this is just pretty smooth. So apply. I believe I might have done the same, or I did 0.01 instead. I think that might be correct. Yeah. So we can generate now. Cool. Now let's check our quality. So you can see this is almost all quad 4. There's literally no tri 3. I mean, or at least it's almost impossible to see. So this is looking good for Fluent. Also our minimum is 0.65, well above the 0.15 min. So our mesh looks good. Now we just have to name the edges. So name this guy inlet. This would be outlet. Jeez. And then all of these will be just our walls. Check our name selections. So inlet, outlet, and walls. Perfect. So that is it for the meshing. Okay, we can update this. Now before I hop into the setup, I'm going to explain the inlet velocity. So we were given how to find the test section velocity. given here, right? So if I find that, so 20, which is the frequency we're working at right now, times 0.2489 minus 0.3718, 4.6062. Now this is our test section velocity, right? We are setting our velocity at the inlet, so we have to find our inlet velocity. We can do that just by, using conservation of mass. So, V inlet times the height of the inlet is equal to the velocity of the test section times the height of the test section, which would be a ratio of 6/22. So we could do, so V inlet would equal, our V test section times 6/22. So times 6 divided by 22, 1.25623. So we can do 1.2562 would be what we input. So we can open up our setup here. Precision is on. Start that. Okay, so now that we're in Fluent, there you go. So all this stuff, you don't have to touch any of this. This is all correct. I'm going to set this to laminar. There you go, laminar. Okay. Our cell zone conditions, we're just going to make sure. Right here, let me just go over the material real quick. So we're just using air. We're just going to keep it, the typical values for air. And then for our cell zone condition, the air should already be applied. Yeah, there you go, but it's always good to check. Now boundary conditions, so everything should already be set. Velocity inlet, pressure outlet, walls. So the outlet here, gauge pressure 0, perfect. Walls, no slip stationary, perfect. Now for our inlet, it's already a velocity inlet, we just have to change the magnitude to 1.2562. So 1.2562, can apply, close, perfect. Now, I believe this is all good. Oh, right, so for reference values, we're just going to do compute from inlet. Make sure you do compute from inlet, because that's, where our velocity is set, of course. So, looks good. Methods, let's check this. Be coupled, yep, second order upwind. Initialization is already set to hybrid, just by default. Now I'm just gonna do like 600 iterations. I'm pretty sure that's a big overshoot, but it doesn't really matter. So now we can initialize and calculate. Sounds good. Residual should dip below, what is it, 1.04. Yeah, well below. Perfect. So that is all. All right. Yes, it is. Okay. Now the rest of the work is done in CFD Post. Okay. Now we'll open up results. And from here it's pretty simple. So I guess a little simple. There is a few things we need to do. So we have to provide contours for velocity, static pressure, total pressure, and dynamic pressure. Now, by default, Fluent includes, of course, velocity and static pressure, which is just the typical pressure variable, right here. This is our static or gauge pressure. So we have to input the dynamic pressure and the total pressure separately. So we can do that pretty simply here under expressions. We're going to right click, new, we can call this first one dynamic pressure. Okay, so we can just put in, the equation for dynamic pressure. So 0.5 times rho, which is of course density. And if it italicizes, that's how you know it picked it up correctly. And then times velocity. Okay, velocity squared. Okay, let's apply this, and now if we apply it and the units are correct, that's how we know we input it correctly. Variable in pascals, perfect. So that is our dynamic pressure. Now we can add another for our total pressure. Now, this is just our pressure, aka static pressure, plus our dynamic pressure, which we just made. Apply. Variable also in pascals. Now let's create the variables for those. So we can start with dynamic pressure. Now do not name it the same thing. It'll throw you an error, so just throw like var at the end or something. So dynamic pressure var. For our expression, we will set that to dynamic pressure, calculate global range, apply. Perfect. Now let's do the same for our total pressure. Oh, right, var. Ooh. Uh-oh. So total pressure. Perfect. Global range. Awesome. So those are our two variables. Now we just have to make the contours, throw our center line, export, and that is that. So let's start with our velocity contours. We're going to compute this from symmetry 2. Variable will be velocity. Our range now. The range, so in my report, I set a user-specified range that was the same for all three cases, specifically to show the difference. If you just let it calculate the range by itself, all of your contours throughout each case, they're basically going to look the same. Like your velocity contours between 20, 40, and 60 hertz are going to look almost identical just because it's, calculating a different range for each. So for actual analysis purposes, I set a specific user-specified range for each case. It was exactly the same for all of them. So for the velocity, in 60 hertz, our max velocity is something around like 15 something. So I set my range from 0 to 16. And this will give us a very blue velocity contour, but if you were to do it in 60 hertz, it would, look quite red. And actually, I guess I will just show that also. So 500, it doesn't really matter how many you do. 500 actually takes a second to compute, but it's okay. So we can apply. There you go. As you can see, it's light blue, turns green where it contracts at the test section. So this looks basically exactly how you'd expect. Now we can do the same for our static pressure contours. So of course this would just be pressure. Set this the same to symmetry 2. Now the range for my static pressure, I had set from 0 to, it was negative 125 to, I believe it was 40. Yes, 40. 500. Apply. Cool, looks orange. Now do total. Let's actually we can do dynamic first. Dynamic pressure contours. Cool. So now here, set this to dynamic pressure var. Location is symmetry 2. My range for this was 0 to 150. Symmetry 2, yes, contours 500. Apply. Nice. Now let's do total. Range for this is negative 125 to 50. Perfect, because static should be 80 out of 40, 0 to 150, 0 to 16. Awesome. So dynamic pressure, static, total. Static and total do look quite similar, but you can see there's a difference at the test section. You'll notice more of a difference in the higher frequencies. And here's velocity. Now, for the data extraction, we have to create a center line. So we'll start location, a point. We can just call this like center line. So, oh, wait, what am I doing? Not a point. Delete. I just kind of blanked there. Sorry. We'll do a line. Call it center line. Okay, there you go. So, of course, it's going to start just at our origin 0, 0, and it's going to run the full length, which this is in meters, and I don't know. I don't remember, at least. So the full length was 15 plus 24 plus 12 plus 42. $78, 93. $2.3622. Yeah, that sounds right. So 0, 0 to 2.2. Wait, what was it? 2.36. 2.3622. Perfect, and it runs the full length. So, okay, so now let's go File, Export, Export. We could just set this to like, yeah, I don't know, center line F20. Type generic. Location, I believe, was set to the center line. Yes, obviously. Yeah, location, center line. Nope, SI units. Now for the variables, since we want to show the variation in velocity, total pressure, static pressure, and dynamic, we can find those in here. So we'll find dynamic pressure, static pressure, total pressure, velocity, and then down here you can also export your X, but it'll export those anyways, at least it should. So we can just go save, and yeah, that's basically it. So that is, yeah, that's really it. So I would just show the other cases now, or I'll just do the 60 hertz case to show the difference in the contours. Now, the best part about, doing all of, creating all the contours, creating the center line and all that prior to changing your velocity is that all you have to do is change the velocity, the contours will be correct, and then you just have to export new data for the different frequency, and that's really it. So this is all good. We can now create a duplicate of this right? Did it make my duplicate? Oh, jeez. There it is. So we'll just call this F40, or sorry, 60B. Not 67. F60B. So everything is basically the same. We just have to go into setup and change our velocity to be the correct 60 hertz. So let's calculate that. Hello, where's my calculator? Jeez, thank you. Okay, so 60 times 0.2489 minus 0.3718. Okay, times 6 over 22, 3.9715. So let's 3.9715. I did that correct, right? Okay, cool. Yeah, so that's correct. Close. Now we just have to initialize and calculate. There you go. Now, if we go into CFD post, okay, let's just close this. Okay, if you go into CFD post, there you go. You can see an actual velocity contour, but of course that's because our velocity is much higher. Yeah, you can also see that our velocity in the center does cap out around the 15 mark, which if I open back up my calculator, if I can find it, right, I think that was our 0.2489 times 60 minus 0.3, what was it, 37? Is 14.5, so yeah, pretty similar around there. And then for our pressure, you see much higher, static pressure and dynamic pressure. And then it's the same exact thing to export the data, just export. Oh, these are still the same, that's nice. And simply just name this 60 instead. Save. And that's it. Then you would just do the same thing for the 40 hertz case, throw your data together, and yeah, that is really it. So thank you. Once again, my name was Hayden Kaliji, ID 5634076. This was project 3 for Dr. Osbey. I did this project solo by myself. And yeah, thank you.